Welcome back, everyone. I'm here in the same notebook as last time. So last time we just created a really simple session graph, and now what we're going to do is create a very simple example neural network just to kind of get the flow. And then after that, we're going to create a full network example. We'll create some artificial data that does follow some sort of linear trend. And then we're going to create a neural network that can solve this regression problem with a cost function and an optimizer. But again, I want to build this up really slowly because if you see it all at once, it looks a little confusing. So we built up this really simple example of a graph that does just an addition operation and a multiplication operation. Now let's build up a really simple neural network. A lot of times in your neural networks, you're going to have a top level cell that has a bunch of constant variable names defined. For example, n features. Your data probably won't change features as you train it, hopefully. So we'll say our data has 10 features to it. Then you'll do something like define how many neurons are going to be in the various layers. Right now, we'll just pretend we have one layer of 3 dense neurons. So we'll say n dense neurons is equal to 3. All right, now we also know we need placeholders and variables. We'll create a placeholder for x. So tf placeholder, and we need to provide in the data type. So we'll say float 32, which is basically what we're always going to be using in this course, unless we specifically have integers. And then we also need to define the shape. So it's really common to say none, because that depends on how big of a batch of data you're feeding into your neural network. And then as the second parameter here, we do know the number of features. So we should expect x to be receiving an array of the number of samples by the number of features. So it makes sense that the rows are the number of samples, and then the columns are the number of features. So typically that's what a placeholder is going to look like. And then you're also going to have variables. For example, we have the w variable for our weights. We'll just say tf variable, and we want to initialize these weights using some sort of randomness. And we'll discuss this later on, what are good ways to initialize weights and initialize the b term or the bias terms. But for right now, we're going to use random normal. That's the random normal distribution that's built into TensorFlow. And then we're going to define the shape of it to be the number of features by the number of neurons in our layer. So in this case, we have one layer, and it's going to just be dense neurons. And we're going to do a similar thing for our bias term. We'll say tf variable, and we can either just have this be zeros or ones. Doesn't really matter for this example, but we'll say tf ones. And in this case, the shape is just going to be number of dense neurons. And the reason for that is because, remember, w is going to be multiplied by x. So for matrix multiplication, we have to make sure that this dimension of columns matches this dimension of rows when you're multiplying it. And then this dimension of dense neurons needs to match up, well, how many neurons you have. As far as the bias term that we're adding in, or that b, we're going to need to make sure that just matches the number of neurons, because we're adding b, but we're going to multiply x by w. So that's the reason we have these specific shapes. So we'll run that. Then we're going to need some sort of operation and activation function. So you'll have something like x times w or wx, doesn't really matter here. And then that will be a matrix multiplication between x and w. Then we'll have z be the output of that. So it'll be tf add x and w to b. So notice here now I'm using those TensorFlow operators instead of just saying asterisk or plus, because I want to make sure that TensorFlow understands that it's doing matrix multiplication and addition. Typically, it's usually smart enough to convert, as we saw up here, these pluses and asterisks, but a lot of times with the documentation, you just want to make sure you're specific that it's TensorFlow. So we'll go ahead and kind of stick with this convention for now. And finally, we want to pass this into some sort of activation function. So we'll say a is equal to tf dot, and there's lots of activation functions available for you. There's the tanh or hyperbolic tangent activation function. There's also, if you do tf.nn dot relu, there's a rectified linear unit, and later on we'll see kind of higher abstractions to just create an entire layer of specific neuron types. But for right now, we'll just do a really simple activation function of sigmoid, and then we pass in z. Okay, so what do we have so far? We define the number of features in our data, dense neurons, the placeholder, variables. Then we said, okay, multiply x times y, or excuse me, x times w, then add b to the result of that, and then pass the result of that into the sigmoid function. Now it's time to run this in a really simple session, and then we're going to say init is equal to tf. We want to say global variables initializer. Run that, and then we'll say with tf.session as sess. I'm going to run the init for the initializer, and then I'm going to say the layer out, that is the result of each of those neurons, is going to be session run a. Remember, that's that kind of final operation that has the rest of those operation graphs in place, or operation graph, I should say. And let's pass in a feed dictionary. So we just have x as our single placeholder, and let's go ahead and feed it in some random values from NumPy. We'll say random, and we'll have it have the shape of 1 by n of features. So I'm essentially just feeding it one sample. So our results are not going to, whoops, let me make sure I have that correct. I forgot to actually make this a dictionary. There we go, curly braces and curly braces. Okay, so our result, as I mentioned, is almost going to be meaningless because this is just a really simple example, more for syntax, but here we have the results layer out of each of these neurons. So again, we had 3 neurons up here, and when we ran this with some random data, your results may be different depending on how many times you ran random, but you should see some sort of results out here, and hopefully you also see that all the values are between 0 and 1 because we're using the sigmoid function. Now the absolute key thing to notice, which is kind of stopping this from solving our problem, is the fact that we're not adjusting the values of w or b. We basically just said, okay, choose some random values of w, have b's all equal to 1, and then run this one time and see what happens out. That is not how we actually run a neural network. We want to then go back and adjust w and b, or our different variables, based off some sort of cost function. So we need to have some cost function and some optimizer in order to adjust w and b. So let's go ahead and now work through a more realistic example of some regression. Just a really simple regression example. So let me now label this as kind of our simple regression example. And this is probably going to be the most realistic example we've seen so far of TensorFlow. Everything before this have kind of been really toy examples or incomplete partial examples. Now it's time to actually kind of dive in. So I'm going to say x data is equal to linspace 0 by 10 by 10. So I want 10 linearly spaced points between 0 and 10. And then I'm going to add just a little bit of noise to it. So we'll say random, uniform, and we'll say negative 1.5 to 1.5 by 10. So then what does this actually look like? Well, it looks like some numbers between 0 and 10 linearly spaced, except we've went ahead and added some noise to it or subtracted some noise to it. So we have these random numbers and we're adding or subtracting them to the linearly spaced points here. So let's actually now plot this out, and we're going to have a label attached to it. So the label is also going to be np linspace 0 to 10 to 10, and then I'm going to add in some random uniform data here, same deal. 1.5, and then let's say 10. Now it's not a huge deal if you don't get the exact same numbers I'm getting here, because what we want to do is have a model that can fit to just kind of some noisy data that has a linear trend. So I want to plot this out to show you what we actually created here. So x data versus y label, and whoops, I forgot to import matplotlib. Let's do that now. We'll say import matplotlib.pyplot as plt, and since I'm in the notebook, I need to say matplotlib inline. Remember, you need to say plt.show if you're not using a Jupyter notebook. Now let's run this, and let's also make sure that we're running it with points. So we'll say asterisks here. Okay, so I have my data, and it looks like some random data, but there's clearly some sort of linear trend here, which makes sense because technically the data is exactly the same, np linspace 0 through 10, np linearly spaced 0 through 10. We just added a little bit of noise to it. So we randomly chose a value between negative 1.5 and 1.5 for each of these points and then added it to it. So your data should be different than mine, or maybe you have the exact same data. that's not really what matters here. What matters is you have some sort of linear trend, and it should be a pretty obvious linear trend. You should start with some lower points and higher points. If you are not getting a trend, which would be extremely unlikely, then just run these two lines again and you'll have a trend. Okay, so we have some noisy data. Let's go ahead and actually create our neural network. To start off, we're going to go ahead and do the following. We'll say, remember, we're kind of trying to solve y equals mx plus b here. So let me actually make this into a comment or something. So there we go. We have y equals mx plus b. So we'll say m is equal to tf variable, and we can go ahead and initialize this. So let's initialize this with some random values. I'm going to say np random ran2. So this is going to give me two random values, and I'm going to initialize m and b to be random values. So again, doesn't really matter if you have the same random values or not for this part. I know I said previously for other sections or other lectures it did matter. Here, I would actually kind of prefer it if you did not have the same values I did. That way you can really see that the neural network is working for any random data set. And we're going to import this right here and pass that in. So the reason I'm doing that is just to make it really obvious to you, the student, that m and b right now are just totally random numbers. So I want you to get two random numbers and initialize these variables as random numbers. It's going to be up to the neural network with the cost function and the optimizer to fix these values to actually create a nice fitted line here. So I'm going to run that. And speaking of the cost function, let's go ahead and create it now. So I will create a variable called error, and currently the error starts off as 0. Then I'll do the following. I'll say for x and y in zip, which is essentially going to make a list of tuples of each point in x data with its corresponding y label. I'll do the following. I will say y hat, which is my predicted value, is equal to m times x plus b. Again, this is just our linear equation here. This is my predicted value. So right now, my predicted value is probably going to be way off because the values of m and b are just totally random. So we need to fix this. And in order to fix this, I need to have some sort of cost function calculating the error. So my error, I'm going to add on the squared error. So we'll say y is the true value. Remember, y is that actual y label. So we're treating this y as the true value. And I'm going to subtract my predicted value, which is y hat. So when we start off, this error is going to be pretty bad because these are random values. So I'm going to measure my error. I'm going to add on this, and then I'm also going to square it to punish higher errors. So again, this is what we want to minimize. We want to minimize this error, which is why this is our cost function. In order to minimize this, we need to use some sort of optimizer, which is step number 2 here. So we'll say optimizer is equal to TF train, and this is where we actually use gradient descent. Remember, we discussed how gradient descent figures out how to best reduce that cost. So if you say tf.train gr, you should be able to tab autocomplete the gradient descent optimizer. The parameter we need to provide our gradient descent optimizer is the learning rate. Remember that the learning rate here basically defines how fast are we going to descent down on this, and if we have too large of a learning rate, then we may overshoot the actual minimum that we're looking for. If we have too small of a learning rate, then it's going to take us forever to actually do that gradient descent. Now, for different problems, different learning rates apply, but right now, let's go ahead and just use 0.001. We can check if it has a default learning rate. I'm not sure if it actually does, but right now, 0.001, that's a pretty common thing to start off with. It really depends on your particular data set, what makes sense. And later on, we'll also learn about things like some more advanced optimization functions. But right now, keeping it simple, we have our optimizer. We need to tell our optimizer what it actually is looking to minimize. So our optimizer is going to have a method called .minimize, and we want to pass in the variable it's trying to minimize. It's trying to minimize error. Okay, so now we have that, and we're actually almost ready to go. What we need to do is create that global initializer for the variables. We'll say global variables initializer, and then all that's left is really to create the session and run. So let's briefly show everything we just did here as a quick review, and then we'll run our session. Okay, so what did we actually do? For the simple regression example, I need some sort of data. I want that data to have some sort of linear form in order for me to predict a simple y equals mx plus b line on this. So what do? I say x data is linearly spaced from 0 to 10 with 10 points, and then I add a little bit of noise to it, also add a little bit of noise to the y label, so I get some sort of fit that's linear, but again, it's noisy, that way it's not just a perfect straight line. So you should have some sort of noisy data set here, but it does just have a general trend to be kind of this line here. Okay, so I want my neural network to solve this equation, y equals mx plus b. So I'm going to initialize it with a random value of m, that is the slope of the line, as well as a random value of b, that is the intercept. And I show that I'm doing it randomly just by choosing the values that this random output. So I want to make sure that you don't think these are some special values that I'm choosing. You should input just some random numbers that NumPy provides you. Then I need to calculate the error, so I need some way to measure how off I am. So I will say, go ahead and predict y hat, and then compare it to the true y label here, square that, and that's going to be my error. Then I need to perform gradient descent to attempt to minimize that error. So I want to optimize this, and that's going to be what the actual trainer is going to be. And then we have global variables initializer. Now let's create the session and run it. So we'll say with tf.session as sess. I'm going to say sess run init. And then now I have to decide how many steps to take. So how many training steps am I actually going to perform? So we'll say training steps is equal to 1 right now. That's probably way too low, but we'll see what happens. We'll say for I in range of the number of training steps, go ahead and say, whoops, scroll down here, session run, and run train. Remember, train is that optimizer is trying to minimize that error. Then finally, I want to fetch back my results. So I'm going to say final slope and the final intercept, whoops, is equal to session run, and I'm going to grab m and b from my session. So I'm going to run this. I would expect this to perform a pretty bad job just off of one training step. Essentially just should be what we started with. Let's go ahead and evaluate the results. And to do this, I will do the following. I will say x test is equal to np linear spaced. We'll go from -1 to 11. This is just for the plot to look a little nicer. And we want 10 points in between that. And then I'm going to say y pred for the plot is equal to y equals mx plus b. So we know I have y is equal to mx plus b. So I'm going to choose the final slope that my model said was good after just one training session. Then I'm going to multiply it by x test, and then I will say plus the final intercept. And let's plot this out. So we'll say plt plot x test data, and then y pred plot. And then I want to grab my actual real data over here. So let's copy that and paste it here. And let's have this be a red line. So I'll say R here. So I run this, and you actually notice after just one training step, it did a pretty good job of fixing those weights. Let's go ahead and run it for, I don't know, let's say 100. It's a really simple equation. You can see it already had a pretty good fit, but if we run it again, then we can see we have a better fit. Okay, so again, let me just do 1 here. It's hard to see the difference just because the data is really easy to fit to, but you can see our line is probably a little off, but when we run it 100 times, we're able to choose better m and b values. Okay, that's really all there is to it for this simple example. Coming up next, what we're going to do is show you an even more realistic example of a TensorFlow regression, and we're really going to kind of hammer this in. And we're going to deal with a pandas data frame, kind of show you what it would look like to read in some data, feed it to the regression, and with a lot more data points, we'll have to feed it in with batches. But for now, go ahead and take this step by step. I would really recommend you check out the notebook and review it, really understand what these last couple of cells are doing here. Okay, if you have any questions, post to the Q&A forums. I'll see you at the next lecture.